for the do now today. So 2 questions here. One of them, you're given the Ksp for manganese hydroxide, and it asks you to calculate the molar solubility. And then in number 2, it says calculate the molar solubility of a saturated solution of calcium fluoride in a 0.01 molar calcium nitrate solution. So if we start with number 1, remember before you even calculate anything, before you calculate Ksp, before you calculate molar solubility, write the equilibrium equation for the solid that they give you. So here, the solid is manganese hydroxide. And because we would classify that as an insoluble solid, it's at equilibrium with its ions. So Mn2 plus and 2 hydroxides. And after you have the equilibrium written, then you can write the Ksp expression. So remember that Sp stands for solubility product. Product is multiplication. So it's the solubility product because you're multiplying the ions that exist when a solid is soluble. So you'd have the concentration of Mn2 plus times the concentration of OH minus squared, because those are aqueous. Ions are always aqueous. And we do not include the solid because we never put a solid or liquid into any equilibrium expression. So if we're calculating the molar solubility is how much of the solid dissolved. Anything at equilibrium, any calculations, we'll set up an ice table. Remember that for the solid, it doesn't really matter how much you start with and how much you end with. You can write sum, you can put a line through it, you can put an X through it. What we are focused on really are the ions. So it says nothing else about there being anything in the solution. There's nothing else in the solution besides the solid that's going to partially dissolve. The change, that's what we're really focused on. A certain amount of the solid will dissolve. Probably not very much, because that's a pretty small Ksp, but some of it will. So Mn2 plus to manganese hydroxide is 1:1. So we would expect to see plus S amount. And then twice as much hydroxide, so plus 2S. And at equilibrium, we would have S and 2S, and that's what gets plugged into our Ksp expression. Because our goal is to solve for molar solubility. So we're solving for S, how much of the solid dissolves. Plug it into the Ksp expression, 1.6 times 10 to the negative 13 is S times the quantity 2S squared. Again, be careful with this algebra, because this becomes 4S squared. 4S squared times S is 4S cubed. And then we solve for S. Make sure you can do cubed roots in your calculator, because you've seen it now between yesterday and today, we've had to do cubed roots. So I'm going to do 1.6 e negative 13 divided by 4. That's 4 times 10 to the negative 14. In my in a graphing calculator, you can hit math 4 and put in your number. In a calculator that looks like mine, like my class set, you hit second and the caret button, it's X root. So how you'd actually type it into this calculator is you would do 3 second caret and then put in your number. Because that 3 in front is telling the calculator that you want to take the cubed root. So the solubility is 3.42 times 10 to the negative 5th molar solubility. When we calculate S out of an ice table, moles per liter or molar, either one. So number 1 was assuming that there was nothing else in the container. It was just the solid. Number 2 says calculate the molar solubility of a saturated solution of calcium fluoride. So I'm going to stop right there. This is the solid that I'm focusing on. Because if it's a saturated solution of calcium fluoride, that means that calcium fluoride solid is at equilibrium with its ions. But we're calculating the molar solubility in 0.01 molar calcium nitrate. Calcium nitrate has NO3 minus. Remember, any ionic substance that has potassium, nitrate, ammonium, or sodium completely dissolves, completely dissociates. So this is a strong electrolyte, meaning it breaks apart completely. So 0.01 molar calcium nitrate means that we have 0.01 molar of Ca2 plus in the solution. So if we think about what's in the beaker, well, we have some calcium fluoride solid down here at the bottom. This is before it partially dissolves. We have some calcium fluoride down here in the bottom. And we have some Ca2 plus, some NO3 minus. So when we think about calcium fluoride, we'll start by writing the equilibrium. Calcium fluoride is a solid at equilibrium with Ca2 plus and 2F minus. Any calculations at equilibrium includes an ice table. So again, the solid doesn't matter how much we start with, doesn't matter how much we end with. What matters is how much dissolves. But if we focus on the ions initially, now in the beaker, instead of it just being solid at the bottom and no ions, now we have Ca2 plus floating around from the calcium nitrate solution. So now initially, we have 0.01 molar Ca2 plus, and we have no F minus. So before the solid breaks apart, we have Ca2 plus from this calcium nitrate solution. So this is a common ion problem. So if calcium fluoride has S amount dissolving, Ca2 plus will increase by S amount, and the fluoride ion will increase by 2S. So then at equilibrium, we have 0.01 plus S and 2S. Oh, I didn't give you Ksp here. I wondered, I was like, why are people looking at Appendix D? I didn't give you Ksp in this problem. So it's the practice with looking at Appendix D. Appendix D, you have this single piece of paper, this coral colored paper. Remember on Appendix D, the Ka values were on the front. This is where we found Kas for weak acids. Up at the top, we had Kb values for weak bases. And all of these values underneath on the back are Ksp values. And so what we can do is we can look under Ksp for calcium fluoride. So calcium fluoride has a Ksp value of 3.9 times 10 to the negative 11. And Ksp for this, did a bad job of writing it before. Here's the Ksp expression. So if we plug everything in, 3.9 times 10 to the negative 11 is 0.01 plus S times 2S squared. Right, the quantity 2S squared. This is a common ion problem. This is practicing with common ion. Now when you look at this and you're like, hey, yeah, that's going to be like a S cubed. Well, remember that if we assume X is small, or S in this case, That lets us neglect that plus S. So this becomes 4S squared. You're squaring both things inside the parentheses. You multiply that by 0.01. Oh. So 3.9 times 10 to the negative 11 equals 0.04 times S squared. So 3.9 e negative 11 divided by 0.04. And I can take the square root of that. 3.12 times 10 to the negative 5th. Moles per liter or molar. And so that's a common ion question. We looked at some common ion yesterday. We'll look at some more common ion today. Today in our examples, I've pulled a lot of the practice questions that College Board has released. So you'll see the scoring guidelines. The ice table is kind of funny for the solid. One of them says, who cares, under amount of solid. So, you know, it's fine. But this is showing you just, this would be in pure water, number one. Number two is in a different solution. So really you're just thinking about in the beaker, just like with titrations and with buffers. What is in the beaker? Do we have anything that could affect equilibrium initially? So what you're going to want for today is your notes packet and a calculator. So keep practicing in your calculator. If you would prefer to actually go through some of these on the desk, you want to use a marker and go through it on the desk, you can. I had some people yesterday that asked if they could do that. I don't care, whatever works for you. There will be some of them that I'm going to have you work on like yesterday. So you can either work through it by yourself, you can work through it with people around you, just so that I'm not, you know, up here doing every single example, kind of breaks it up. So before we get into examples, to try to answer some more questions of what affects molar solubility in KSP. So video 8.6 talked about this top point. So a common ion will affect molar solubility. The pH of a solution will affect solubility, and the formation of complex ions will also affect solubility. Common ion and complex ions are two totally different things. Complex ions are they're no longer tested. They used to be tested on the AP test, not anymore. So I briefly mentioned it. Essentially what happens with a complex ion is you have a metal, so something like Fe2+, that can actually form this complex ion with other substances. A lot of times we see it with water. And it's pulling the metal ion out of solution to create these complex ions. And so by the metals forming these complex ions, now we don't have enough metal. So more solid has to dissolve. But complex ions are no longer tested. We will be focusing on common ion and the pH of a solution. So we've looked at common ion already yesterday in one of the examples, and today in the do now. We'll also focus on pH. A lot of times the pH is just a common ion question if you have hydroxide in your solid. So if you're looking at weak bases. Other times we'll look at how solubility can increase or decrease in an acidic solution, and that's more conceptual. So we'll focus on the conceptual ideas as well. And then 8.7 focused on determining if a precipitate is formed. As soon as you see the word precipitate, you should immediately write down Q versus K. So as soon as you see that it says, will a precipitate form, or determine if a precipitate forms, right? Anything like that, immediately write down Q versus K. And then just like before, we've looked at Q versus K. If Q is greater than K, so you can think about those bar graphs that we looked at. So the first one, if Q is greater than K, here's Q, here's K. Well, remember, to be at equilibrium, Q needs to equal K. And so to get back to equilibrium, Q needs to decrease. And so the reaction will shift toward the reactants. The reverse reaction will occur. And if it shifts back toward the reactants, that's a solid, we would say precipitation occurs. So if Q is greater than K, that means you have too many ions. And so the reaction will shift back to the reactants, which is a solid. So a precipitate will form. I think in the video I talked about being removed from solution. If you're thinking about precipitation, a precipitate will be removed. It's a solid. So solution, you have ions. Precipitate is a solid. If they equal, so if Q equals K, then we're at equilibrium. We call that a saturated solution. In this top one, this would be considered a super saturated solution. So if you've ever seen the, well, let me get one. If you've ever seen the hand warmers that you crack the little metal disc and the solid forms. Right, like this. Sixth period today. All right, so in these, this is a hand warmer. And if I break the metal disc, you can see that the solid is forming, right? And then it gets warm. So it's an exothermic reaction, but a solid is forming. That was because this was a super saturated solution. So there were actually too many ions in this solution. So when I made this small change, it caused precipitation. It's very warm on my hands. So this would be a super saturated solution, too many ions. When Q equals K, this is a saturated solution. We're at equilibrium. And then if Q is less than K, so if you think about these bar graphs again, here's Q, here's K. If Q is less than K, we are not at equilibrium. We are only at equilibrium if Q equals K. Remember, Q is at any time. They give us concentrations, we plug it in, that's Q. It's K if we know we're at equilibrium. So to get to equilibrium in this bottom scenario, if Q is less than K, this is an unsaturated solution. There are not enough ions. Think about an unsaturated solution like watery Kool-Aid. Right? You don't have enough of something in the solution. And so to get to equilibrium, Q needs to increase. You need more ions. And so more solid will dissolve. So just a reminder that Ksp is equilibrium. Qsp, right? So that Sp after Q just means that we're comparing it to Ksp. Just like Qc we could compare to Kc. Qp we could compare to Kp. But Q is calculated from initial concentrations or concentrations at any point in a reaction. If we don't know if we're at equilibrium, that's a Q calculation. But you're going to be able to tell because it's going to specifically ask, will a precipitate form? And when you see the word precipitate, that means Q versus K. So we'll jump into example 6. For example 6, calculate the molar solubility of manganese hydroxide. And they gave us the Ksp. So we're calculating the molar solubility of manganese hydroxide at 3 different pHs. Now, if we think about what is in the beaker, all right, we're thinking about what is in the beaker. So for each one of these, it's going to be different amounts, but for each one of these, we have manganese hydroxide as a solid down here in the bottom. This is before any equilibrium is established. We have manganese hydroxide down in the bottom. If it just said pure water, then we just calculate it like we did in number 1 of the do now. Now they're giving us different pHs, which is telling us that we have a certain amount of OH minus in the beaker. And if you look at this, you say, well, why did you do OH minus and not H plus? Because I have OH minus right here. This is nothing more than a common ion problem. So let's start by writing the equilibrium for manganese hydroxide. Manganese hydroxide is a solid at equilibrium with Mn2 plus and 2 OH minus. If I write the Ksp expression, it's Mn2 plus times OH minus squared. So for part A, we have a pH of 7. Okay, well, here I kind of gave a little hint. The OH minus concentration is determined by the pH or POH. We have OH minus, and we say, okay, well, pH can give us OH minus. We can figure out what that is. If the pH is 7, what's the POH? 7. So the OH minus concentration is 10 to the negative 7. So the OH minus concentration that we have in this solution is 10 to the negative 7. Now I'm going to just do my ice table kind of right underneath here. I'm going to do that for each one just so I don't rewrite this every single time. So again, it does not matter how much solid we have. We have no manganese 2 plus in the container. But we do have OH minus. We do have OH minus. Now again, if this said pure water, we wouldn't worry about this. Right? Yes, pure water has a pH of 7, but we're not adjusting the pH of the solution. So now we're going to say, okay, minus S plus 2S. Looks like this. And then if we plug into our Ksp expression, 1.6 times 10 to the negative 13 is S times 1 times 10 to the negative 7 plus 2S quantity squared. Could make for a very rough algebraic expression. Or, how do I get to ignore this 2S? Assume S is small. And so what that does is that lets us ignore this plus 2S. Now that doesn't mean that we don't have to square it still. Still have to square it. But we can ignore that plus 2S. So 1 times 10 to the negative 7th squared is 1 times 10 to the negative 14th. So then to solve for S, I just divide it over. I know your answer is not wrong. It's 16. We have people that say, but this is a big number compared to what we've been looking at. So we have 16 moles per liter. Well, now we can do the same thing for B and C. So I'll set it up, and then I'll have you guys kind of work through. I'll work through it on the board as well so we can check. But if the pH is 9.5, what would that make the POH? 0.5? So the OH minus concentration is 10 to the negative 4.5. Because remember, 10 to the negative pH or 10 to the negative POH is how we can find the concentration. So now we have our hydroxide concentration. Do you have to set up the ice table? If you can just use this one as guidance, no. Or you could just plug it right into the Ksp expression. So squared. So there's part B. So as we added a common ion, we added more OH minus here. If you notice the amounts. We increased the amount of OH minus. That decreased the solubility. Yeah.
Would you get 3.16 times 10 to the negative 1?
I did 10 to the negative 4.5.
Okay.
So if you just left it as 10 to the negative 4.5 and plugged it in, that's fine.
Okay.
I just did in my calculator, like I did second log to get 10 to the x and then did negative 4.5 to get that number. Yeah. So. I'm just going to plug it in for part C. I just use the ice table for part A and B kind of as my guidance for part C. When you do 10 to the negative 2.2, you get 0.00631. So that's where that number comes from. I assume x is small. What I get for the solubility for part C is 1.51 times 10 to the negative 9th. Did I square that? Nope. Hold on. Did not square. That's why I looked at that. I was like, nope. Oh, that's why. Got it. No. 1.6 e to the 13 divided by. There we go. 4.02 times 10 to the negative 9. Let's see, I don't remember getting that number when I worked through this one. 4.02.
What is it?
Did you square this number?
Yeah.
So I did. So I got 1. So 1.6 times 10 to the negative 13. And then when you square this number, it's 3.981 times 10 to the negative 5th. So I did 1.6 e negative 13. Not negative 9.
I forgot it.
Okay, it's fine. I forgot the 1 and 1.6. That's how I got 1.5. So notice as we increase the amount of hydroxide, we increase the amount of common ion. And if you say, how do you know this is a common ion and not something to do with pH? Well, always start by seeing what would be in the beaker. If you have a common ion, it's going to be a common ion problem. As we increase the hydroxide, so we went from -7 to -5 to this would have been -3 in terms of the exponents. As we increase the hydroxide, solubility decreased. So the common ion effect says that increasing the common ion, as you increase this amount, right, you now have too much of it, the reaction is going to shift back toward the reactants. It's going to reduce solubility. Questions on this example? Yeah.
I had to. Okay, so at the very beginning, we started with the pH, and then we got the OH concentration.
Yeah.
Why did we put it? I thought the pH was at equilibrium.
So you could do it at either one.
Okay.
We are saying that, so this is the pH of this solution at equilibrium, and then we put the solid in. So we had a certain hydroxide concentration. We're thinking about like having two things being added together.
Okay.
So we have this solution that had a certain hydroxide concentration at equilibrium, and then we had this solid that got put in.
Oh. Okay.
Since it shared a common ion, we put it as the initial. If you did it as equilibrium, you would actually get the same thing because we neglect the S anyways.
Right. Okay.
So either way would actually be okay. Yeah.
Okay.
All right, so I want to have you guys see if you can solve example 7. So this is also a common ion problem. And in your notes, I actually gave you this what's in the beaker picture. So I actually put this picture into the example. So example 7, you'll have to flip pages in the notes. But this example says, calculate the solubility of strontium oxalate. So you want to underline strontium oxalate because if it's asking you for the solubility of that, that is your solid that exists at equilibrium. Now, if you notice over here in this picture, it actually gave you the equilibrium already. So you have strontium oxalate at equilibrium with its ions, Sr2 plus and C2O4 minus. But it wants you to calculate the solubility in a solution that has 0.02 molar sodium oxalate. I gave you the Ksp for strontium oxalate. So here you have this saturated solution. You have some solids still on the bottom, but you have Sr2 plus and the oxalate ion. Well, when you have sodium oxalate in there, you've added a common ion. So set it up like we've done. You have your ice table, but now instead of both of the ions being 0 initially, you're going to have oxalate. So see if you can solve. For example 7, you're solving for the solubility. You have your equilibrium here. If it helps you to rewrite your equilibrium equations, you can do your ice table underneath it. You can do that. Write the Ksp expression. Think about what gets plugged in. So once you're done, I put the, so here's where it's funny, the teachers that were making these scoring guidelines for College Board, I like their ice table. Right. Some, who cares? Right, what we're focused on is the solubility. That's why we've been putting -S on the solid side just to remember that it's dissolving. But you can see the ice table. These are just 1-to-1. Plus S and plus S because strontium is +2, oxalate is -2. We assume that S is small. That's why this S is negligible. So when we plug it in, Ksp equals S times 0.02. And we solve, we get 8 times 10 to the -6 molar or moles per liter. Solubility, when you calculate solubility out of Ksp, it's moles per liter or molar. Either unit that you pick is up to you, but you have to give one of those two. Questions on this example? This is a College Board like practice question, so you can see not much more than what we were doing yesterday. So here's one that's conceptual. So the fluoride ion F- has been added to water to help prevent tooth decay. There's actually an entire line of chemists, right, who are dental chemists, and their job is to actually do work with like enamel decay and tooth decay and figuring out ways to use Ksp to cause precipitation back onto teeth. An experiment was performed to study the solubility of calcium fluoride in tap water. Solubility of calcium fluoride in pure deionized water is 8.58 times 10 to the negative second grams per liter. So this is the solubility of calcium fluoride if it's just pure water, no common ion. Would the experiment be predicted to result in a higher or lower solubility for calcium fluoride in fluoridated tap water? So just to add to this, here's what this means. F minus in the water. All right, F minus in the water. Let me move my hand over. So instead of it just being pure water, you have F minus. So that means that you're adding a common ion. So notice it just wants to know, would it result in a higher or lower solubility for calcium fluoride? So would more or less solid dissolve justify your answer? This is a conceptual question. So you always want to start with either more than or less than. So I'm going to leave this part blank. I can just write than, right? This is either going to be more or less. Now let's just kind of write through what we know. So we know that this fluoridated tap water has F minus in it. So the fluoridated water contains F minus. So I'm just kind of talking through how this would affect solubility. So I'll say F minus is a common ion. Now there's two ways that you can do this. You can talk about the Chatelier's principle, or you can talk about Q versus K. Either one works. So you could say there's too much product. So the reverse reaction will occur, reducing solubility. Or you can talk about Q versus K. So we can say, since F minus is a product, this results in Q greater than K. If you're adding F minus, you're changing equilibrium. So now it's a Q versus K problem. So Q would be greater than K. Too many products. So this would cause the solubility to decrease. Solubility decreasing means more solid and less ions. That's what that means. So if the solubility decreases, we would expect the number in fluoridated water to be less than. This is a conceptual question where you're thinking through what would happen. It didn't ask us to calculate it. It just wanted to know, will this result in a higher or lower solubility? Or you could say it'd result in a lower solubility. All right, lower than 8.58 times 10 to the negative second.
On one of the videos last night, you said adding more H plus can result in less H plus.
Oh, we'll look at that in, I think, example 10.
Okay.
So when you're talking about an acidified solution, you're adding H plus, and it's going to result in solubility actually increasing at a certain time. Yeah, so that's actually in one of the later examples when you're looking at adding an acid. So like adding H plus to this would have an effect because F minus is a base, which is actually why.
So it's not the same thing. Adding more F to this situation is not the same thing as adding more H plus.
No, because adding F minus is adding a common ion. Adding H plus, that would be if you acidified this solution.
Okay.
So if the solution was acidified, it would result in different solubility than if you're adding a common ion. Yeah. Yep. Okay, so if we look at example 9, I'm going to have you guys actually try example 9. So I want you to try example 9 on your own. I'm going to work through it up here as well. So if at some point you want to look up and just check to make sure you're on the right track, that's fine. But this is a common ion question. It's a regular Ksp question. You can tell that this is a sample free response question. And so go ahead and work through it. If you want to kind of talk to people around you, that's fine. So you're just writing a balanced equation, calculate the solubility. Right. Unless it really specifies, you're calculating molar solubility. And then part C is where the common ion comes in. So work through this. Just remember, ions are always aqueous. I know I haven't been good about putting AQ after the ions. I will tell you, people see this 2 liters and they think they need to do something with it in part B. You don't. You don't need to do anything with that 2 liters in part B. So I've got A and B on the board so far. You want to check as you're going through. So I have part 1 of C up here. This is where that 2 liters comes in. You can see I calculated sodium fluoride concentration first. It's moles per liter. Got moles per 2 liters. There's 2 liters of solution. That got me my concentration of NaF. It's actually the same as the concentration of F minus because it's a 1-to-1. And then from that, part 2, there's your common ion question. So now you go back through like you did in part B, but now you have a common ion. So for example 9, I did right A and B over here, part C number 1 over here. So that was just calculating the molarity. And then number 2, you are using part 1 to answer part 2. So if you miss part 1, remember that does not mean that you miss the points for part 2 because it's conditional. So if for this, let's say that you just divided this by 1 liter. And so you got 0.06. Well, you would miss the point for part 1, but if you use 0.06 in here and you solved, even though this would be an incorrect number, you did it correct based on previous information, so you would still get the points for part 2. All right, so free response questions are always graded conditionally. So if we take a look at, oh, there's the answers. We take a look at number 10. So this is answering the question, what happens in an acidic solution? So when we are looking at solubility, we've been focusing now on common ion. Well, we can also look at what happens when we put solids into acidic solutions. So this is answering the question, what happens when you add a plus? Well, if we take a look at this example, it says, which of the following salts will be substantially more soluble in acidic solution? So for this example, we're looking at which of these would be much more soluble if we put it into an acid than if we put it into water. So this is what we kind of go off of with acidic solutions or acidified solutions. When we have a salt, if the anion of the salt is a base, so if it's a weak base, when we put it into an acidic solution, that weak base will react with acid and will actually be removed from solution. So in this case, we're talking about being removed. It's reacting. It's going to be gone. It's reacting and forming something else. And so let's just take a look first. Let's just classify parts of these salts. So we're focusing on the anions. So in each of these, we're focusing on the anions. And our goal, because remember the anion of a salt comes from an acid. So we want to see what acid does it come from and what does that mean about the anion of the salt. So CO3, 2 minus, would come from H2CO3. Is H2CO3 a strong acid? No, it's not one of the 7 strong acids. This is a weak acid. Well, remember you have one of 2 pairs, strong neutral or weak weak. So if H2CO3 is a weak acid, CO3 2 minus is a weak base. Let's look at part B. We have S2 minus. That would come from hydrosulfuric acid, H2S. Is H2S one of the 7 strong acids? No. So this is a weak acid, meaning that S2 minus is a weak base. I minus. I minus comes from HI. Is HI one of the 7 strong acids? Yes. Right? HCl, HBr, HI. Those are 3 of the strong acids. Well, if HI is strong, that means that I minus is neutral. CN minus comes from HCN. Right? HCN, not a strong acid. Which means CN minus is a weak base. And PO4 3 minus would come from H3PO4, also a weak acid. Therefore, this is a weak base. So first, if the anion is a base, it will react. So we have A, B, D, and E. C, we can cross out. So the ones that are more soluble are ZnCO3, ZnS, AgCN, and A3PO42. Now I'll show you why. I'll use zinc carbonate to show you why this works like it does. So if we think about zinc carbonate, here's the equilibrium of zinc carbonate with its ions. Now, if we add an acid, or it's an acidic solution, that means that we're adding H+. And you look at this, you're like, well, there's no H+, so how is this going to react? Well, CO3 2 minus, because it's a base, will react with H+. So what we will actually have is we'll have CO3 2 minus reacting with H+ to create HCO3 minus, and then we can add another H+ to create H2CO3. But as carbonate is reacting with H+, we are reducing the amount of CO3 2 minus in solution. So as a weak base reacts with H+, reacts with an acid. So that's what a base does. A base reacts with an acid. CO3 2 minus, we have less and less of it in this equilibrium because it's reacting and forming something new. So because we have less CO3 2 minus, more solid will dissolve. More solid dissolving, we would say it's more soluble. You have more solid dissolving. So that's why A, B, D, and E are all more soluble in an acid because they all have a base as part of their salt. It's a weak base. I minus is neutral. It's not going to act like a base. It's not going to react with H+. So the 4 that are more soluble are the ones that had the bases. That's what we look at with solubility in an acidic solution.
Is there a way to determine which of those 4 is the most
will become the most soluble? It would depend on the concentrations of the bases. That would result, then you have to do ice tables with the bases.
So there's no conceptual way to figure that out.
there's no mathematical way to figure it out. Like, if you want to know which one of these.
Yeah, like so like they would never ask the question out of those four.
No, they would ask a question that more like the one, what was it, example 4 yesterday? 5 yesterday with that table. You know, which of the following was more soluble, where they give you Ksp and you just solve for solubility.
Okay.
Yeah. All right, so then if we look at example 11, and we might just finish a couple of the examples tomorrow, because I want to give you some time to work on mastering today. For example 11, so we're at least going to do 11 and 12 because it's talking about precipitation. And then 13 and 14 might be good practice because it's going to kind of pull everything together. So we might do that tomorrow. So example 11, will calcium hydroxide precipitate? So before you even keep reading, underline precipitate. Because if it's asking, will calcium hydroxide precipitate? That means Q versus K. As soon as you see a question say, will it precipitate? That's a Q versus K question. And then you can keep reading. So if the pH of a 0.05 molar solution of calcium chloride is adjusted to 8.0. So they really are kind of giving us 3 different things here. Because they're asking us if calcium hydroxide will precipitate. So that means that this is the solid I'm focusing on. So I'm just going to go ahead and write my equilibrium. I'll worry about the math after. So I'm writing the equilibrium of the solid that it's asking me about. Will calcium hydroxide precipitate? And the Ksp expression, Ca2 plus times OH minus squared. So when it's asking if something will precipitate, that means we're calculating Q. So underneath here, I'm going to actually go ahead and I'm just going to rewrite Ksp, but I'm going to rewrite it as Qsp, just so I remember that now we're calculating Q. And when you're looking at will something precipitate, you are taking the information that they are giving you. Take the concentrations that they give you, and that's what you plug into the Q expression. So they give us information about Ca2 plus from this solution of calcium chloride, and they give us OH minus by giving us pH. So over here, I'll just say the concentration of Ca2 plus. So we have a calcium chloride solution. Calcium chloride is actually soluble. It's a strong electrolyte. It'll break apart completely. They should have given us like calcium nitrate, but so the concentration of Ca2 plus is equal to the concentration of CaCl2. How do I know? Because for 1 calcium chloride, there is 1 Ca2 plus. So in my Q expression, notice I do not have an ICE table because I'm not focused on equilibrium. I'm using the information that they give us. I'm using the current conditions to compare Q to K. So Ca2 plus is given to us from calcium chloride. OH minus will be based on the pH. So if the pH is 8, what's the POH? 6. Be careful. Do not use 8. That is pH. So if I want the OH minus concentration, that's 10 to the negative POH. So my OH minus concentration, 10 to the negative 6, this 1 times 10 to the negative 6, and that is squared. People say, well, why do you use the Ksp if it's not at equilibrium? Well, the Qsp expression is the same as the Ksp expression. But instead of solving for K, we're solving for Q. We're figuring out, are we at equilibrium? So 0.05 times 1 e negative 6 squared. So Qsp is 5 times 10 to the negative 14. Suppose I should have K. I'll give you guys K. Ksp is 6.5 times 10 to the negative 6. Again, on a test or a quiz, they would give you Ksp so that you can compare it. So, how does Q compare to K?
Less than.
It's less than. So Qsp is less than Ksp. So with the question, will it precipitate? Think about if Q is less than K. Well, if Q is less than K, to get to equilibrium, reaction is shifting this way. Which means we need more ions. So when you're thinking about will it precipitate, you want to know, will a solid form? In order for precipitation to occur, Q has to be greater than K. I'll say, so no precipitation. Right, no precipitate will form. No precipitate will form because we did not have like too many ions. Q was not greater than K. Q is actually less than K. So at these conditions, right, we actually need more ions to even get to equilibrium. So the last example that we're going to look at for today is example 12. So example 12 says, will a precipitate form? Oh, well, that works because it's still pretty much underlined. Will a precipitate form? So I'm going to leave precipitate underlined up at the top. Will a precipitate form means Q versus K. Now this one's going to make us think a little bit, which is why I put this in our examples. This is a practice question. It kind of ties in some dilutions as well. So will a precipitate form? I need to compare Q to K. If 0.5 liters of a 0.25 molar solution of KCl is slowly added to 0.5 liters of a 0.25 molar solution of PbNO3(2. This is the Ksp of PbCl. Here is the solid that we are focused on. So the solid that we are focused on here is PbCl. The information that they gave us up here is telling us that we are mixing KCl and PbNO3(2. We are creating a precipitation reaction. But the solid that we are focused on, that's at equilibrium with its ions, is PbCl2. And the reason that we still want to write that reaction is because we want to write the Ksp expression. Because for a precipitate to form, we still need to compare Q to K. And the Qsp expression is the same as the Ksp expression. So now what is the Pb2 plus concentration that we're plugging into Q, and what is the Cl minus concentration that we're plugging into Q? However, before we plug anything in, We are adding volume to volume. When you add volume to volume, you're diluting. So I need to figure out what is the new concentration of KCl and what is the new concentration of PbNO3/2. The reason I need to figure out these new concentrations is because we are diluting these solutions. We are mixing them together. So M1V1 equals M2V2. M1V1 equals M2V2. So KCl, we start with a 0.25 molar solution of KCl that's 0.5 liters. I'm trying to figure out what's the new molarity when these two solutions are mixed together. 0.5 plus 0.5 is 1 liter of solution. All right, so you can do M1V1, M2V2. The new molarity of KCl is 0.125 molar. Again, the reason that we are doing this is because we are adding two solutions together. So we are finding the molarities immediately before they react, like we did with neutralization reactions. So then for lead 2 nitrate, 0.25 molar, 0.5 liters. Oh, so that's actually the same molarity. So our molarity is when the volume changes. 0.125 molar of each. So there's our KCl and our PbNO3/2. This is important because this is telling us what concentration of Cl- do we have to plug into here, and what concentration of Pb2+ do we have to plug into the Ksp expression. So Qsp, right? It's no longer K. We don't know if we're at equilibrium. We're using the concentrations that were given to find the ions. Now this is KCl, just in case you want to see the ratio. For 1 KCl, there is 1 Cl-. So the molarity of Cl- is 0.125 molar. This is the molarity of PbNO3/2. Well, for 1 PbNO3/2, there's 1 Pb2+. So it's the same concentration of Pb2+. 0.125 molar. So we can do 0.125 times 0.125 squared. Qsp 0.00195. Put it in scientific notation to help. 1, 2, 3. 1.95 times 10 to the negative third. There's Q. How does Q compare to K? It's greater than K. So if you think about Q is here, K is here. To get to equilibrium, the reaction shifts back toward the reactants, back toward the solid. If the reaction shifts back toward the solid, you're making more solid, precipitation occurs. So will a precipitate form? Yes. When Q is greater than K, a precipitate forms. So as soon as it talks about a precipitate, we want to focus on Q versus K. We'll save examples 13 and 14 for tomorrow. Just kind of reviewing KSP tomorrow. So for the rest of today, about 15 minutes. You can, if you want to start working on mastering, right? Start working on mastering. Make sure that you grab the study guide. And if you want to grab the practice test right now, it's over on the side. So the study guide's in the top tray. Practice test is on the side counter. I would suggest reading through the study guide first. The study guide is all just information. The practice test has the video answers like the last review did. That's all on the website already. The only thing really in terms of homework, work on the mastering. I tried to split the questions based on the videos, but now we've watched all the videos. Read through the study guide. Remember, lab is due tomorrow. So kind of mastering and lab are the two things. There is additional KSP practice if you want extra practice, page 9 and 10 of the notes. So there's an extra like practice page.